Alright guys, this is Virtual Algebra 2, section 4.4. This is the last section of chapter 4 that we're going to work on in this unit. We're going to finally apply all of our matrix knowledge to solving systems of equations, which is, if you remember, way back before fall break, before everyone scattered out of Madagascar. That was sort of the point of this whole unit, was solving systems of equations. So we're going to figure out what the connection is between this kind of stuff that we were doing weeks and weeks ago to the stuff we've been doing this week with matrices. Okay? So you can probably already think of a couple different ways to solve this. What different ways did we learn? Right? We could graph it and find where they intersect. We could use substitution, or we could use elimination. All right? And then finally we can use matrices. Now you see the way I've got these written, x and y are both on the left side of their equation, and on the right is just any constant number that's left over. If you want to solve systems using matrices, that's the form you want to put everything in, right? Some x and some y equals a number, some x and some y equals a number. Alright, so the first step is just translating this into a matrix equation. So the way it works is we're going to have a matrix of coefficients. Then we're going to have the unknown matrix, xy, and that's going to be equal to the stuff on the right-hand side. Okay? So I bet you can guess what goes in that coefficient matrix. How many x? 3x. How many y? -1. -1, 2. Okay, so stare at that for a second. Can you see why this is equivalent to this? Right, because you need to be able to do that. Translating from this to this is the first important step. Right? I mean, you can almost just kind of see the equation here. 3x minus y equals 2. Negative x plus 2y equals 7. Right? So it's not really hard, but it's important. Okay, so once we've done that, then we have a situation very familiar to us, right? We have a matrix equation we want to solve for this. What was the trick we learned? Right, we're going to multiply both sides on the left by the inverse of this matrix. So our next big job is going to be, let's find the inverse of that. You remember how to do that? Well, of course you can use your calculator, but you can also find the determinant, 6 minus 1, 5, and then play the game with switching things around. The 3 and the 2 switch, and these two change signs. Okay, so there's our inverse matrix. 1/5 times 2, 1, 1, 3. We could also write it as 2/5, 1/5, 1/5, 3/5. It doesn't really matter which way we do it. Okay, now we're going to multiply this equation on both sides by this inverse matrix. Okay? So it's going to be our inverse matrix times our original, and we know what that's going to give us. Pretty soon you're going to stop even writing that step out because you know that this is designed to give you the identity matrix. It's actually a good idea to not skip that step because it's a way to check whether or not you've done your inverse correctly. And we can't forget to multiply by the inverse on this side as well. Always on the left. Okay, I'm running out of space. I'm going to go to another segment here. You try that multiplication on both sides and see if you can get it to work out. So, you multiplied out the right-hand side, and hopefully you got 11/5 and 23/5, right? And that is the answer. That means that x is equal to 11/5 and y is equal to 23/5. We could check that in the original system of equations by plugging in those values, and you can go ahead and try that, and it does work. So just to review the way this kind of problem works, if you're given a system like this, you can rephrase it as a matrix equation. Okay, then you're going to have to find the inverse of this coefficient matrix A, and if you multiply both sides on the left by that inverse matrix, On the left side, that's going to cancel out with the coefficient matrix to give you the identity matrix, which then doesn't need to be there. And so we have X isolated. And on the right side, we have whatever A inverse times C happens to be. In this case, it looked like this, and it gave us our answer like that. Okay, now this seems like a lot of work. You're probably thinking, I could have done this a lot easier, a different way. But the good news is that this does work on your calculator, okay? In fact, if we get beyond 2 equations and 2 unknowns, I would never ask you to do this, except using your calculator. Finding the inverse of a 3 by 3 or higher order matrix is just terrible. And no, you shouldn't have to do that by hand. Let me just show you a really nasty example. Can you see that? Supposing we had 5 equations and 5 unknowns. Oh my gosh, A, B, C, D, and E, right? 5 equations here. All right? We could build a matrix equation like this, based on that. Okay, and here's our unknowns, A, B, C, D, and E. And we have all our coefficients in this box here. Now, I don't even know how to find the inverse of this matrix by hand, but I know that the calculator does know. Okay? And so, if I find the inverse of this matrix A and multiply it by this matrix B, I'm going to get the answer. Okay, and there it is. -4, -2, 2, what is that, 8 and 8? All right, you can try that, and it actually does work. It works no matter how many equations and unknowns you have. An interesting thing about this is that, as we know, we can only find the inverse of a square matrix. And that is another way of nature telling us that if we have 5 unknowns, A, B, C, D, and E in this case, we're going to need 5 equations. If we don't have 5 equations, there will only be, say, 4 equations, and there would only be 4 rows here. This matrix would not be square. It would not be invertible. This problem would not be solvable. Okay, so for each new variable you add, you need some new information. You need a new equation. Right? So this kind of math is called linear algebra, and it goes way on from here. But you've just seen one of the most important things that I know about linear algebra. This matrix stuff was invented, as I think I said at the beginning of this chapter, by physicists who were studying atoms and molecules and very small, strange things. All right, so there's just a couple more issues to clear up, and then we're done with this. And the first one is, well, how would a system with no solutions look using matrices? Or what about a system with many solutions? You know, because when we did way back at the beginning of systems, we talked about systems where there was no solution, where the 2 lines were parallel and never crossed. Systems where there was one solution, where the lines crossed and there was one answer. And then systems where the 2 lines overlapped and there were an infinite number of solutions. So what do these 2 cases look like? Right? This is the kind where you just get an answer, the kind we've been working on. Okay? Well, in matrix world, what's going to happen is that you're going to get the determinant of your matrix to be 0. Okay? If the determinant of the matrix is 0, and if the inverse is 1 over the determinant times whatever, switched around matrix numbers, I mean, this right here tells us that we're not going to get a defined answer for this inverse. And so, in fact, you can't take the inverse of a matrix with a 0 determinant. So that could happen, and your calculator might give you an error like this. It might say error singular matrix. That means the determinant is 0. You cannot invert this matrix. Okay, and so it could be that that means there's no solution. And the only nasty thing here is that, as far as I know, you're going to get this same error whether you have 2 parallel lines that don't meet or 2 lines that are on top of each other, hence an infinite number of solutions. So this error is going to tell you there's something funny about this problem, and you're going to have to investigate using other methods to find out if it's this or this. Okay? All right. Well, I think that about wraps it up for Chapter 4. I'm going to give you some homework. Practicing solving systems using matrices. Okay, page 248, 11 to 35, odd.